Okay, in this video, we're going to be talking about power functions. And by definition, what we mean by a power function is any function of the form f of x equals some number, and that number can be 1, times x to some power. Okay, to where that nth power could be a first power, a second power, a third power. It could be a square root of 2 power. It could be a 1/2 power. So let's now look at some common monomial functions that are power functions. A power function is also a type of monomial function, meaning it's a one-term function. Draw a sketch of each of the following monomial functions. So let's look at our monomial power function that is a constant. That'd be f of x equals some constant c. And that would, of course, be x to the 0 power there. Anytime you have a constant function, like y equals 2, y equals 3, y equals 4, that's always going to be a horizontal line. Your next power function, or your power monomial function, is f of x equals a linear function. We'll just do f of x equals x. So therefore, x to the first power, it's going to be, we know it's linear. It's going to have a y-intercept there of 0 because it is a monomial function. You don't have that plus 2 or plus 3. Your next monomial function here is going to be f of x is equal to x to the second power, and that's our most basic parabola. We've seen those before. Cubic function, f of x is equal to x to the third. So our power function is to the third power. Looks something of this form. Quartic, f of x is equal to x to the fourth. Now this is going to look a lot like your quadratic function. The only difference is it's going to be a little bit flatter and it'll spike much quicker because you're raising those powers to a fourth power instead of a second power. So we know that we'll raise 2 to the second power, we get something like 4. However, if you were to raise 2 to the fourth power, you'd get 16, so growing much quicker. Quintic function, f of x equals x to the fifth power. Looks a lot like x to the third power, but kind of the same scenario. It's going to flatten out more there around 0, 0, and look something to that effect. Symmetry in these functions. And we've kind of discussed this symmetry before. If the function has an even power, then it is symmetrical about the y-axis. Now I'm going to put in parentheses, it would be an even function. If it's symmetrical about the y-axis, we remember f of negative x equals f of positive x. It's an even function. It's symmetrical about the y-axis. Some examples up here. X to the fourth power, x to the second power. We're both even functions. So the next one, if a function has an odd power, x to the first, x to the third, we see a couple of examples up here, then it will have rotational symmetry, which means you can rotate this function 180 degrees and it's going to be the exact same function back. So if it has an odd power, then it has rotational symmetry. So again, it will be symmetrical about the origin and it will be an odd function. And we remember the test that would actually confirm that f of negative x would equal negative f of x. So let's look at some end behaviors of these power functions. You have an even power and a positive coefficient. If the number out front is a positive number, which in this case is a positive 1, your end behavior is going to look like this. And as x approaches positive infinity, your graph will always go up. So y would approach positive infinity. And as x approaches negative infinity, you get the exact same thing. Y is going up to positive infinity. Now, what happens when we put a negative in front of it? When our coefficient is negative, then our end behavior, we know that this is a vertical flip. It would flip it across the x-axis, and our end behavior looks a little bit different. And now, as x approaches infinity, our graph is going down, so our y would be now approaching negative infinity. And as x approaches negative infinity, or as we go to the left, our graph also goes down, so y would be approaching negative infinity in that direction as well. Again, our odd power functions, we remember kind of the basic shape of x to the third, x to the first. Here's our x to the third. It is an odd power, but the positive coefficient out front would force it to look like this. And our end behavior is now, as x approaches positive infinity, your graph will always go up. So y will always approach positive infinity. And as x approaches negative infinity, your graph goes down. So y would approach negative infinity as well. Again, as soon as you put that negative coefficient out front, we have a vertical flip. So my graph now looks like this, and my end behavior looks like this. As we travel to the right on these graphs, my function goes down, so y would approach negative infinity, and as we travel to the left, my function goes up to positive infinity. Okay, next up, we're asked to graph power functions, and in this first one, we're going to graph 3x to the 6th power and identify some of its characteristics. So let's plug in some points, or plug in some values here on this graph. The easiest ones being 0, 1, and -1 that we can plug in. When I plug in 0, I'll get 0 in this case. When I plug in 1, raise it to the 6th power, multiply by 3, I get 3. So 1, 3. And when I plug in -1 to the 6th power, I get 1 times 3 would also be 3. Now plugging in, if you were to try to plug in anything else like 2 or -2, this is going to be so far off the graph, it's not going to fit. 2 to the 6th power is going to be 64, and if you multiply by 3, you're going to get 192. So again, not going to fit. So you could plug in maybe values like 1/2 if you want some more points just to see what this graph's going to do. And if you were to plug in 1/2, when you raise it to the 6th power, you get 1 over 64, so you would get 3 out of 64, which is a very, very tiny value. So you can see now why it's so flattened right there around that 0. So your 3x to the 6 is going to look something to that effect. Let's do our characteristics. Your domain, anything can be plugged into this function. So my domain is negative to positive infinity. However, my range, my lowest point is going to be 0, and it's going to increase forever in both directions. My y-intercept and x-intercept are both going to be at 0, 0, or at the origin. Increasing interval is going to be everywhere from 0 to infinity, and it's going to decrease everywhere from negative infinity up to that 0 point downhill. It's going to have the symmetry about the y-axis because this is an even function. It's an even power. Discontinuities, there are none. There's no breaks. There's no jumps in behaviors. And we should know these in behaviors eventually by heart. But if it's an even function, as x goes to the right, your y will go up. As x goes to the left, your y will go up as well. The only thing that would cause, again, that even function to have a different in behavior is if the number out front had been a negative. It would have flipped it across. Here we have negative 2x to the 5th. Again, we're going to plug in some basic values and see where this graph goes. And here I've plugged in 0, got 0, plugged in 1, I got -2, plugged in -1, I got +2, and it's going to look something like this. And again, notice how flat. It's going to be really flat right around that 0 value. Your domain and range here, domain, you're going to be able to plug in anything. And notice your graph continues down and up forever with no breaks, so your range would be all reals as well. Your x and y intercepts, again, are both going to be the origin, is where it crosses. Increasing interval, notice my function starts out decreasing, and it decreases down to that origin, so we'll do that first. So it's going to decrease from negative infinity to the origin, and then it's going to increase from the origin past, or on to positive infinity. This is an odd function, so it's going to have rotational symmetry. So it's going to be symmetrical about the origin because, again, it's raised to an odd power. Discontinuities, there are none. In behavior, again, this is a classic in behavior because it is an odd function, and it has a negative out front, which means it flipped it down. So as we go to the right, our graph will go down, and as we go to the, that'll be negative infinity. As we go to the left, our graph will go up. Negative 1/2 x to the 4th. So here we have our x to the 4th, which normally would look like this. However, since the negative's out front, it will flip it down. So we kind of know the basic shape here. Let's plug in some points and see what it's going to look like. Again, it kind of has that basic upside down parabolic shape. I did get 5 points to fit here. Plug in 0, you get 0. Plug in +1, you get -1/2. -1, you also get -1/2. Plug in +2 gave me -8, and plugged in -2, it also gave me -8. So my domain here, I can plug in anything. My range is going to be all values always start with the lowest. That'd be negative infinity up to 0, which is going to be your origin there. Your x and y intercepts, again, are both going to be the origin. The region where it's increasing would be from negative infinity up to its highest point at 0, and then it starts decreasing, and it decreases forever. Symmetry, this does have y-axis symmetry. It's symmetrical about that y-axis, again, because it's an even function. Discontinuities, again, there are none. In behavior, and again, this is always characteristic of an even function with a negative coefficient. The even function makes it parabolic shaped. The negative in front flips it down, so as we travel to the right, my graph goes down, and as we travel to the left, my graph goes down. So there's your end behavior.